Okay, class, I want to do a few more problems. I've gotten several questions by email and several questions during office hours about critical points. So it seems that you guys are okay with the d-test and using the d-test to find local extrema. Your issue is solving a system of equations to get the critical points. So I want to work just a couple problems. I think this will help us clarify some issues. So the first one is f of xy equals x to the fourth plus y to the fourth minus 4xy plus 1. And we want to find the CPs. And then you'll take it from there with those CPs if you're trying to find local extrema or global extrema in places with horizontal tangent planes. This CP's answer will help answer those questions. But for this particular problem, x to the fourth, y to the fourth, minus 4xy, we're going to see that this is an easier variation. And then the second one I want to work is where I think the issues are coming in. So f sub x, no problem. So nice power rules, 4x cubed minus 4y, set that to 0. F sub y, again, nice power rules, 4y cubed minus 4x equals 0. And this is a system, two equations, two unknowns. It's a system of nonlinear equations. They are interlocking because you can't just quickly pull off values of x and y, but what makes this one a little bit easier, even though they are an interlocking system of nonlinear equations, you can solve for one, like say the first one, if we factor out the 4, x cubed minus y equals 0, so we can say y equals x cubed. That represents the first equation, and we can plug that into the second equation, and we'll see where we get from there. So taking, this is again 1, forcing that into equation 2. We'll take that, stick it right here. Let's maybe factor out the 4 out of this one. We do the same thing just to make it a little bit easier. So y cubed minus x equals 0, but y is really x cubed, so this will be x to the 9th minus x equals 0. Factor out an x. So we see right away x equals 0. And then x to the 8th minus 1, the only way that can happen is if x is positive 1 or negative 1. So we get 3 solutions for the x value, but each, to make a critical point, you need an x and a y pair. Now remember how x and y are linked. That was back from the solved equation over here. So very easy to see that when x is 0, y is 0, and that makes a CP pair, the point 0, 0. When x is 1, y is 1, makes another critical point. And when x is minus 1, y is minus 1. So you get 3 CPs from that. Every time you have a CP, you can always go back and check, does 0, 0 actually satisfy? So you would need f sub x of 0, 0. You plug in, does it give you 0? That's the question. If it does, good. You need to check the other half. Does that equal 0? Yes, it does. Okay, so that's a CP. I noticed some folks were maybe trying to like match a 0 and a 1, maybe, let's say. So x equals 0, y equals 1, and trying, is that a CP? So you would check if x is 0 and y is 1, does that work? And you'd plug in to your partials, and you'd see that that is not going to give you 0. So 0 for x and 1 for y gives you minus 4, which is not 0. So not a CP. I don't even have to check the other one. Question. So you can't mix and match them in this way. There are some instances where you can, because you have the first equation just gave you some x stuff, the second equation just gave you some y stuff, let's say, and then you can kind of make all possible combinations. Doesn't work in this instance. So I think this is actually one I believe most of you could handle. It's the next one that I think causes some issues. All right, so I'm going to go ahead and move on to the next one. Pause the video, take notes if you need, and email me with more questions. Otherwise, we're going to change up the function. And let's look at this one. 10x squared y minus 5x squared minus 4y squared minus x to the fourth minus 2y to the fourth. Yeah, okay. That one we want to find the critical points. Once again, nice polynomials, no problem taking partials. These are really basic. That's not the issue, right? For you guys, it's solving the system that results after I get these partials. So f sub x and f sub y. With respect to x, we're going to get 20xy minus 10x minus 4x cubed equals 0. The second one, we're going to get 10x squared minus 8y minus 8y cubed equals 0. All right, and once again, we have a nonlinear system of equations that are interlocking. We have x and y's that are sort of tangled together, and we have to see, can we untangle them? And some of these it's easier to untangle than others. The second equation, there's nothing we could factor. I mean, you could take the 2 out, I guess. So we have 5, 4, and 4. Doesn't really do anything algebraically for us, get us anywhere, but maybe that'll help us down the line. The second one we could, or sorry, the first one we could also factor out a 2, but we can factor out an x as well. So let's see what happens. Go ahead and take out the 2 first. So we'll have 10, 5, and 2. All right, and then we'll factor out an x. So we'll just have 10y minus 5 minus 2x squared. Okay, and from that, we can see right away that x equals 0 will solve the first equation. And then we wonder if x equals 0, we'll put that into the second equation and see, do we get values for y? And then we'll have a pair that is a critical point. Okay, so again, x equals 0. This gives us two factors, x equals 0, and then this more complicated factor, 10y minus 5 minus 2x squared equals 0. Let's start with the first one, x equals 0. What happens with, so we know x equals 0 solves this first f sub x equation. We need to figure out what are values that help us solve the f sub y equation. So we'll start with x equals 0, we're sort of fixing that, plug that in here, and we see then we're left with this equation. So we can factor out minus 4y, and we're left with 1 plus y squared equals 0. Now we can solve that. First thing we see is, and again, remember that'll happen when x was 0, and then we see y is 0. The second factor doesn't give us any real roots, so we're not interested in those. So we do get one critical point, our first one, critical point of 0, 0. Okay, now let's take the second equation and see what we're going to do with that one. If that equals 0, then we know the first equation is solved. So we're going to see what happens if we force that to be 0. Maybe it has something to do with the relationship between x and y. And we do see, like, we could easily solve for y here. So let's do that in this second factor of the f sub x first equation. And then we'll take that and plug it in here and see what happens. So I'm going to remove this so we have some space to work on this one here. So let's see. Actually, you know what? Rather than solving for y, I think just looking at these two, I think it's going to be a whole lot easier if I solve for this x squared, because I can just plug that in right here, rather than have to do it in several places and cube something. So I think it'll get us to the same place, but I think it'll make our algebra easier. So I'm going to solve this for x squared. So that means x squared is on this side, 10y minus 5 divided by 2 there. So that is x squared is 5y minus 2.5. And again, when that happens, when that is the relationship between x and y, which we forced by design, that means the f sub x equals 0 equation is solved. What we're going to do is take that, this representation of x squared, and shove it in right here. By doing that, we see that we've now taken an equation, a nonlinear equation of one equation of 2 variables, and it will now become one equation of 1 variable. They'll all be in with respect to y. So I'll have 5 times this, so that'll be 25y minus, what is 5 times 2.5, that's like 12.5, I think. Minus the 4y, minus 4y cubed, equals 0. And okay, so this is one equation, one nonlinear equation, but it is a cubic equation. So maybe there's hope that we can get solutions to this. Let's see, I can clean up. I'll really just have 21 y's, right? And then I just like to put the cubes first, so I'd like to write it like this: 4y cubed minus 21y minus 12.5 equals 0. So that is a cubic equation. In class they made you memorize the quadratic formula, right, to solve a quadratic equation. There exists a cubic, a quartic, and a quintic. They get more and more complicated. But typically what is done, again, you can use a calculator or a tech tool. We'll do those in a moment. But what you're going to get once you do that are roots that solve this equation. And often those are done, the tech tool or the calculator is, rather than using this cubic or quartic or quintic equation, that actually a little historical tangent, like Cardano and Tartaglia in the 16th, 17th century, they spent a lot of time working on these kind of making extensions of the quadratic formula. But typically what happens with modern tools is that you're going to use things like Newton's method or numerical methods. Another good class, Math 245, if you haven't taken it yet, to figure out how do you solve these things numerically, because often there isn't a closed form expression that you could just crank away on algebra. It doesn't exist. So, I mean, you can sit there and try for pages and pages, but you're never going to get to that. You could on this one. Again, you could if you were Cardano, wanted to work out all this. Probably have lots of crazy roots in there. But we're going to use a numerical method and get values for this. And just the big picture, once we get those values for y, we know that that would solve the f sub y equation to get its corresponding partner to make the x value in the critical point pair. We would come back to this equation and solve it. We take the value of y that we got, we plug it in here. We'd see that we're probably going to get a plus minus. Every y will have a plus and a minus x. So we'll get a couple more critical points to add to our list over here. And then we would know by design that those, like if y was 5, solve this, we put 5 in here, we got 2 values for x. We have like a positive 3 and a 5, a negative 3 and a 5, and we just keep adding some. We would know by design that they solve these in the critical points. Okay, so here's where we're at, the cubic equation. So a couple things you could do. You could enter the function, this part, into a calculator as like y equals a function of x into your TI, your favorite TI calculator. Of course, replacing these y's with x's and graph it. And what would you be looking for? To solve this, then you'd be looking for x-intercepts, right? Because again, let's just be clear about it. You'd be entering y as a function of x, which is 4x cubed minus 21x minus 12.5. Enter that into your calculator, and then you're just looking for the shape of it and like, where does it cross? There. Okay, those are roots then. Those x-intercepts are places where it has a height of 0. So those are your roots of this equation. They're part of our critical point. So that's one thing you can do. The other thing is you could just go to a tech tool like Wolfram Alpha and ask it to solve this equation. And again, what it's really doing behind the scenes is a technique that you would learn in Math 245, which is, again, super cool class because most textbook problems, they're so nice and well behaved in that you just do enough algebra and there you get to this nice clean answer of 1, 2, or if it's nasty, 5 halves. But what really happens in real life is crazy decimal answers, and you can't do that by hand. First of all, you can't even factor these things by hand. They don't exist. If I give you an x to the 6 power equation, there is no closed form explicit formula for that. So you're going to have to rely on tech tools. And then how do you know how to check your work? Again, some discussion of that that we'll be having later in the semester as well. Okay, so I'm going to share the screen. We'll go to a tech tool. Let's see. Let's do Wolfram. Solve 4y cubed minus 21y minus 12.5 equals 0. And again, by rules of polynomials, things you learned before, well, look how crazy. Again, that's a closed form solutions. It looks like that's using Cardano's cubic equation. Really crazy. How did people even invent this? But there's approximate form. So let's see what those three, it looks like there are 3 roots. Again, that's what we'd expect, a maximum of 3 roots, because that's the power, right? Rules of things you learned about polynomial functions. And then here's the graph, just showing what the function, the other way I showed you, you just put in your calculator, TI calculator. These are where it hits the x-axis. So it's over here around -2, I don't know, -2/3, and over here at like 3-ish. Oh, and here's our precise values. And they can, Wolfram Alpha can even give, like, you can ask it for even more, oh yeah, more digits, boom. And then you can even ask for more beyond that, like it'll just keep on running them out. So here we see, let me just put 2 decimal places just to keep it easy on the board here. So we got, this thing solves and we get 3 roots. Y is approximately -1.898, it looks like, minus 0.647, and one more, y is about 2.545. 3 decimal places of accuracy there. Okay, and then once you have those, let's stop the share for a moment. Once you have these, you need to go back and put them in here to get your corresponding x value. And let's see, I think I already did that, so I'm not wasting time on those calculations. Let's see. This first one, when I plug that in, I get 2 different values, because again, you take the plus minus. So x is approximately the plus minus of 2.64. The second one, x again gets 2 roots. It's about plus or minus 0.86. And then this third one, when I plug in, actually doesn't give me any real roots. So there's nothing there. And now I can add to my list of CPs over here when x is 2.64 about. Again, you can carry as many decimal places of accuracy for whatever application you're working on. And then y, the corresponding y was 1.898. And then we take the negative x and pair that with the negative 1.898. And then there's 2 more. Negative 0.86 and positive 0.86 pairs with the y of negative 0.647. Again, this example is another one of just how difficult, even though it was a basic function, basic partials, no problem, how quickly solving a system of nonlinear equations can get complicated and difficult. And maybe complicated isn't the right word, just sort of technical, because yeah, we've got all these decimals in there. Now, how would you check if this is all the ones that exist on this function? Or even check that what you've got makes sense? Once again, if I want to check the second CP, I plug those values for x and y right here into my partials and check that I get 0. Depending on how many decimal places of accuracy, you'll get something really close to 0. Okay, that's what we want. Another way is you would graph this thing with a tech tool. So it'd be a good idea to pause the video, go to CalcPlot3D, put this one in, and you'll see that you do indeed get horizontal tangent lines at these 5 spots. And these are either maximum or saddle points, and you find that out with the d-test, which again, I feel like you guys were pretty comfortable with. All right, well, hope that helps, and then just send me if you got more questions.